Howdy everyone, and welcome to lecture 36 of MEEN 410, MEEN 611. So again, my apologies for the audio video issues that we had in class the other day and needing to do this video lecture recording a little bit later than when you ordinarily would have gotten this content, but nonetheless, here we are and we'll be able to share all the same information that you would have gotten otherwise. Okay, to get started, there's just a couple of announcements to share with you. First of all, a reminder that Lab 3 is due Wednesday, April 27th, this coming Wednesday. We'll have gone through all of the material that you need to write objective number 1 for Lab number 3 after today's lecture, and we'll be starting the material that you'll need for objective number 2 today. Maybe finish it. I don't think we'll finish it today, but we'll for sure finish it on Monday with lecture 37. Also, Lab 4 groups will be assigned today for the MEEN 410 students, and then for both 410 and 611 students, Lab 4 handout will be posted today as well. Okay, so I also want to take a little bit of time to talk about the Exam 2 details. We've already talked about this a little bit in one of the lectures this past week, but just to kind of give you a review or rundown of where we are with the rest of the semester. So we're essentially right here with lecture number 36. And of course, Lab 3, as you know, this has been pushed to a due date of Wednesday, April 27th. And so that's been updated on the calendar. We're about a lecture behind schedule where we'll be wrapping up the flame temperature characteristics today. We'll be starting and probably finishing the fuel air cycle analysis development today, and then probably covering the fuel air cycle analysis characteristics on Monday. This will then allow you to do all of Lab 3, right? So once we get through the fuel air cycle analysis characteristics, you'll be able to do objective number 2 of Lab number 3. And then on Wednesday, we'll probably start our discussion about SI combustion and burn rates. And this here is what you will need to do for Lab number 4, as well as Exam 2. So Exam 2 is basically covering much of the material that we'll talk about in those 3 lectures about SI combustion and burn rates, and some other cumulative type things that we've discussed throughout the semester. I wouldn't be surprised, for example, if you're asked a question about power generation, or if you're asked a question about nitric oxide formation, like what we'll be talking about here in just a minute as related to Lab number 3, or discussing things related to efficiency and such. So related to that, about Exam 2, you'll notice that Exam 2 is scheduled for Friday, May 6th, and it's obviously scheduled for 8 a.m. to 10 a.m. That's our scheduled final exam time slot. But as I've already mentioned in class, we'll be making Exam number 2 a take-home exam, and I haven't quite yet decided on all the details, but it'll probably be released on Thursday, May 5th at noon. So Thursday, May 5th at noon, and then you'll have 24 hours to complete it, and so it'll probably be due on Friday, May 6th. Also at noon. So you'll have 24 hours to complete it. And again, it'll only take you 2 hours to write it, but you have the 24 hours to work around schedules and other things of that nature. So these are still tentative at this point, right? This could change, but that's currently what I'm thinking. Now, in preparation of Exam number 2, there is a review session, Exam 2 review. And so in one of these days leading up to May 4th, I'll be sharing with you a sample exam that'll essentially be very similar to what you'll see with Exam number 2. And then ordinarily, I would be able to go over that review with you in person, but regrettably, I'll be on travel on May 2nd, May 3rd, and May 4th. And so I don't know yet about May 2nd. I'm going to try and see if I can schedule my flight such that I leave later in the day on May 2nd and can still teach class the morning of May 2nd. But definitely I'll be out of town on Tuesday, May 3rd and Wednesday, May 4th. And so I'll need to move these 2 lectures to being online, including that review session. And so I'll have that posted for you by the May 4th timeframe. Okay, so this is basically our end of the semester. Things very quickly are coming to a close, and trying to get all of the various items done and make sure that we cover all of the relevant material that you will need for your lab number 4 as well as exam number 2. Okay, so let's go ahead then and continue on with the actual lecture material and wrap up our discussion about adiabatic flame temperature. And so if you remember, when we last had class in person, we essentially generated a figure that looks something like this, where we have adiabatic flame temperature as a function of phi equivalence ratio, right? So we have our adiabatic flame temperature here on the left-hand side on the y-axis, and then of course phi is over here on the x-axis, okay? And so this is our equivalence ratio. So as you can see, generally speaking, as what we drew in class, our adiabatic flame temperature tends to increase on the lean side, reaches a peak, and then begins to decrease as we go to a richer mixture. And of course, I'm not going to go over those details since we went through all of that in the previous lecture. And then we also talked about how increasing the exhaust gas recirculation level, the EGR level, will cause a lowering of the flame temperature, right? And if you remember, we discussed that the reason for this lowering of the flame temperature as EGR increases is we're essentially diluting the mixture with mass that has to be raised to the same temperature of the reaction temperature, but it doesn't actually provide its own energy to the reaction. So it's in concept very similar to leaning the mixture with the say diluted air, right? As you go to lean equivalence ratios, increasing the EGR level is more or less doing the same thing. But the difference, though, is that rather than using pure oxygen or air, for example, to dilute your mixture at lean equivalence ratios, you're using exhaust gases to dilute your mixture. And so you have increased concentrations of CO2 and water in your mixture. And as a result of that, that causes your peak flame temperature to shift closer to stoichiometric, right? So if you look at where that peak flame temperature is occurring, you'll notice that generally the peak flame temperature is shifting closer and closer to adiabatic, where this, of course, is the stoichiometric. This is the phi equal to 1 equivalence ratio, and the peak, of course, is just shifting closer and closer to a phi equal to 1. And so one of the chief reasons why that happens is because, if you remember, we talked about how as we raise the equivalence ratio up to stoichiometric conditions, the adiabatic flame temperature continues to increase because we're decreasing the concentration of O2 in our products of combustion. And so as that O2 concentration decreases, the mixture goes to a higher temperature because there's less mass there to absorb the energy. And so your mixture temperature ends up reaching a higher temperature. But then as we begin to go beyond stoichiometric conditions, we eventually reach a peak, and then our decrease in adiabatic flame temperature is at a lower slope than the rise in adiabatic flame temperature on the lean side. And of course, we explained that in class to be the result of the rich products of combustion have increased concentrations of species that absorb less energy than the products of rich lean combustion. And as a result of that, they are able to keep the flame temperature bolstered higher as equivalence ratio increases and their concentrations increase. So then why is it that this peak, and that also, just to kind of complete that thought, that also explains why the equivalence ratio at which peak adiabatic flame temperature shifts from, say, a phi point of, this is perhaps phi equal to 1.1, and this is perhaps a phi equal to 1.08, and maybe this is 1.05, and maybe this is 1.02, for example. And so so then the question is why is that shift occurring? Why is the equivalence ratio getting leaner, or at least closer to stoichiometric, as the EGR level increases, right? Well, To explain that, we first recognize that the reason why this peak flame temperature occurs at an equivalence ratio rich of stoichiometrics, say a phi of 1.1, is because as we increase the equivalence ratio, there ends up being a shift or a balance in, say, the equilibrium between CO2, CO, and oxygen, as well as, say, for example, the relationship between water, H2O, and hydrogen, and, say, oxygen, for example, right? And so we end up having, as we go to higher and higher flame temperatures, this dissociation reaction is pushed in the forward direction, right? As you go to higher flame temperatures, your carbon monoxide concentration increases, as well as your oxygen concentration, okay? And CO absorbs less energy than CO2 does, okay? In other words, CO2, because it's a more complex molecule, is able to absorb more energy within the molecule itself than CO or oxygen is able to absorb. Likewise, water is a complex molecule, and as you raise its temperature, the water dissociates into H2 and O2. So as we go to higher and higher flame temperatures, as the equivalence ratio increases, there's a dissociation of H2O into H2 and oxygen, and these two species, H2 and oxygen by themselves, hold less energy at a given temperature than water does. And consequently, because these molecules hold less energy, that energy has to go somewhere, and so it goes into raising the kinetic energy of the whole mixture, which is to say it raises the temperature of the mixture, okay? So as I raise so this peak flame temperature occurs essentially where there's a balance between the dissociation of CO2 and water into their component species of CO, hydrogen, and oxygen, okay? And over addition, if you will, of there being higher amounts of mass within the mixture, right? So eventually the temperature begins to decrease as there's an overabundance of, say, CO or hydrogen atoms within the products of combustion. And so what causes this shift as EGR level increases, what's causing that shift is that the dissociation, right? And so the extent of dissociation of CO2 and H2O into component species. So that would be things, for example, like CO and H2 decreases as temperature decreases. In other words, equilibrium is being shifted toward the reactants. So as we raise the flame temperature, we're dissociating CO2 into CO and oxygen. That causes the shift in where that peak flame temperature occurs because CO and oxygen absorb less energy than CO2 does, resulting in an elevation of the temperature of the mixture. And so as we increase the EGR level, we decrease that temperature. We shift the equilibrium in the reverse direction so that now there's less CO and free oxygen in the mixture. There's more CO2 in the mixture. And so that CO2 is able to absorb more energy, not only lowering the temperature, but also causing this where this peak occurs, since that balance between the change in the composition of the species versus having more mass in the mixture is shifting toward the stoichiometric condition, okay? And so the shift in the equivalence ratio of peak adiabatic flame temperature occurs due to the lowered adiabatic flame temperature shifting equilibrium toward reactants. Okay? Okay, so that's essentially everything that you'll need to address on this particular slide, the relationship between adiabatic flame temperature and equivalence ratio, as well as the impact of exhaust gas recirculation on both flame temperature as well as this shift in where the peak flame temperature occurs, okay? Okay, and so now what I'm going to actually do is jump ahead 2 slides and go to the relationship of mole fraction of carbon monoxide as a function of equivalence ratio. And as you'll notice, and as might be expected, as we increase our equivalence ratio starting from a lean condition, say for a 0% EGR case, the carbon monoxide concentration begins to increase, of course, rather drastically as we go to richer and richer conditions, right? And so we can essentially argue, right, that so for the relationship mole fraction of CO as a function of equivalence ratio, so what do we have going on here? Well, remember that there's, well, let me back up a minute, right? So the first observation that we see is that that CO concentration begins to rise lean of stoichiometric, right? Notice, for example, we have a non-zero concentration of non-zero concentration of CO at an equivalence ratio of 0.8, right? And so what happens is as temperature, as T adiabatic increases from a lean condition, dissociation of CO2 and H2O into their component species that is CO, H2, and O2 occurs more fervently, right? In other words, another way of saying that is that equilibrium shifts to the products as temperature increases. So again, if we look at our dissociation reactions, we have CO2 is in equilibrium with CO and oxygen, right? And H2O is in equilibrium with H2 and oxygen. And of course, what happens is equilibrium is being driven to the products as temperature increases. Okay? Okay, so that's one explanation, right? And so what's basically happening is you begin to see these initial increases in carbon monoxide, even for lean conditions like 0.6 and 0.8, because the flame temperature is high enough to cause that dissociation of CO2 into CO, for example, okay? But then how do we explain why carbon monoxide fraction continues to increase, right? So if I were to overlay on here the flame temperature, in fact, let me do it this way. If I were to overlay on here the flame temperature behavior, what I would get, is something that looks like the following. So I'm going to mark on here where I would expect to see peak flame temperature, right? And so adiabatic flame temperature essentially looks something like this. That's poorly drawn. Let me see if I can do a better job with that. we go. That's better. Okay. So if we look at this region here, right, we might argue that what's going on this side is CO increases, certainly because temperature is increasing. Okay. But then how do we explain the continued rise in CO after we reach our peak adiabatic flame temperature, right? Our peak adiabatic flame temperature is occurring at 1.1. And so if we accept the fact that our CO concentration is increasing because our increasing temperature has shifted equilibrium toward the products, then how do we explain the ever-increasing CO as we go to a richer and richer mixture where now the flame temperature is decreasing, right? Well, if you remember, when we first talked about equilibrium, we said that there's three things that can affect equilibrium of a mixture, right? The composition of the mixture that's in equilibrium, where the species of the mixture are in equilibrium, okay? The first one was temperature, and so we've already addressed the temperature effect. The second one is pressure. Well, our pressure is basically staying the same here, or we can reasonably assume that it stays about the same. So then the third issue, or the third item that can affect equilibrium, is species concentration, okay? And that's what's causing this ever increase in the CO concentration as we go to richer and richer species, right? And so on the rich side of our peak adiabatic flame temperature, we have increasing species concentrations, causing the continued rise in CO, despite a decreasing temperature. And again, you might be thinking, okay, well, what is that increase in species? Well, remember that our fuel is a hydrocarbon, right? And so as we go to richer and richer mixtures, we're increasing the concentration of carbon in the reaction, in this equilibrium reaction, right? As we increase the fuel concentration, we're increasing this concentration of carbon. And so as we add more and more carbon, because adding carbon, so if you have a mixture of CO2 with CO and oxygen, if you add more and more carbon, that's going to have a tendency to shift the reaction in the forward direction. Okay, that imbalance in carbon is going to make it more difficult to create fully oxidized carbon, right? Fully oxidized CO2. And so by adding species to the mixture, by adding carbon, you're also shifting your equilibrium to the right. And so as carbon concentration increases, the equilibrium reaction will also be shifted toward the products, okay? Okay, so that'll allow you to answer the relationship or address the behavior of CO as a function of equivalence ratio. And of course, now what's really nice about this plot and why I discuss it next is you see what the effect of increasing EGR is on this relationship, right? In other words, as we increase the exhaust gas recirculation level, your CO concentration gets smaller and smaller for any given equivalence ratio, right? And so, of course, the EGR effect is that as we increase EGR, adiabatic flame temperature decreases, causing the equilibrium to shift toward reactants. Right, so again, we have CO2 is in equilibrium with CO and oxygen. And as we lower the temperature, that's going to cause the reaction to favor the reactants, right? So lowering of temperature favors the reactants. Okay. Okay, so that pretty much addresses everything that we need to discuss as related to mole fraction of CO. So let's go ahead and talk now about one of the really interesting behaviors to study with adiabatic flame temperature, and that is the relationship of nitric oxide with equivalence ratio, right? So this is NO as a function of phi, and just again as a very technical disclaimer here, just recall that the mole fractions of NO, right? So NO concentrations are equilibrium concentrations. So these are based on an equilibrium reaction. Oops. Let me go ahead and correct that real quickly. Not on kinetic reactions. And so again, equilibrium reaction is a purely thermodynamic chemical reaction where we go from one state to another state, and the reactants and the products are allowed to achieve their equilibrium states, their equilibrium conditions at both states. Kinetics, however, is a time-dependent relationship where you may or may not actually achieve equilibrium concentrations during a kinetic reaction, right? There may not be enough physical time for the kinetics to drive the reaction toward an equilibrium condition. Okay, so these NO concentrations that you see in this plot here are all mole fraction nitric oxide equilibrium concentrations. Okay, so it's rather interesting because you'll definitely see similar behavior if we were to repeat these calculations using kinetics. At least for engine applications, we would actually see very similar relationships, which I'll talk about in just a moment. But I just want to make sure that everyone understands that these are, in fact, equilibrium concentrations, not kinetic concentrations. Okay, so one of the first things that you'll notice right away, if you take a look here, this is our stoichiometric equivalence ratio, right? And so notice what's happening, that the peak NO concentration is occurring very lean of stoichiometric, right? And so let's kind of talk about that first to understand exactly what's going on. And really, it again comes back to these three principles that drive equilibrium, right? And so if we now look at the NO concentration as a function of equivalence ratio, right? And we're basically getting a relationship that looks something like this. Okay. And this is NO concentration, YNO. This behavior is resulting from two competing contributors. Of NO formation. Of course, you'll remember, and we talked about this in class a couple of times, you'll remember that nitric oxide is a very strong, has a very strong dependency on temperature. So that's the first competing contributor. And then, of course, the second competing contributor is species, right? So again, remember that two of the three conditions that'll shift the equilibrium of species are temperature and species, right? And so the reason why we're seeing this behavior with the NO is due to competition between the temperature of the mixture causing dissociation of N2 and O2 into nitric oxide, and then secondly, the species, okay? And so let me go ahead and write out what that equilibrium reaction is. So basically, our reactants in this case would be N2 plus 1/2 O2, and this is in equilibrium with NO. And real quick, you might be wondering why I wrote N2 and O2 as the reactants and NO as the product, whereas before when we did carbon dioxide, I had carbon dioxide as the reactant and carbon monoxide and O2 as the products. The reason why is that this CO2 in equilibrium with CO and 1/2 oxygen is basically as you add energy to CO2, it'll dissociate into CO and 1/2 oxygen. Whereas as you add energy to N2 and O2, it'll dissociate and form NO. Okay, and so this is why we generally write it this way. And so another way to think about it is that if we want the temperature effect to be in the same direction, right? And so as we add temperature, so as temperature increases, we're going to shift equilibrium to the right, okay? But likewise, as we add concentrations of N2 or O2, we will also shift the reaction to the right, okay? And this is where there's a competition, because when we're at lean conditions, right? So if I go ahead and draw on here, say as a function of equivalence ratio, and suppose this is the adiabatic flame temperature, and suppose this is the mole fraction of N2 and mole fraction of O2. They're basically the same. Their relationship is the same. And so our adiabatic flame temperature would look something like this. So this is T adiabatic, right? Off of the T adiabatic scale. But then if I plot the mole fraction of N2 and O2, that's going to look something like this. Right? And so this would be either the mole fraction of N2 or the mole fraction of O2, right? And so using the second y-axis. And so essentially what you see is that at very lean conditions, I have plenty of nitrogen and oxygen, but I don't have a high enough temperature to dissociate them so they can form NO. Then as I go to my stoichiometric condition, I have a high enough temperature to dissociate N2 and O2 into NO, but I don't have any N2 or O2 to dissociate into nitric oxide. And so where this peak occurs is basically where there's a trade-off between having enough species and having enough temperature. So if I'm lean of this point, I have enough species but not enough temperature. And if I'm rich of this point, I have enough temperature but not enough species. And so my peak nitric oxide concentration occurs where that trade-off is balanced, right? Where that equilibrium is formed, where as I raise temperature, I'm shifting my equilibrium in this direction, but I'm decreasing my concentrations of N2 and O2, which is having the tendency to shift the reaction back toward the reactants, right? And so this is essentially what happens as phi increases with our nitric oxide as a function of phi relationship, okay? Okay, so that's basically why you see this relationship that you do, right? So the NO concentration rises as we have plenty of species, and the temperature is increasing, and it continues to increase as temperature increases despite the falling concentrations of available species. And then finally, we reach the peak where we've got sufficient temperature and sufficient species. But then as we increase equivalence ratio, our temperature continues to increase, but now our available species decreases. And so our NO concentration precipitously decreases as the number of available species to dissociate decreases, okay? And then, of course, that you can also now see why that would explain the decreasing nitric oxide relationship as we go to increased levels of EGR, right? So as EGR increases, adiabatic flame temperature decreases. And so from an equilibrium point of view, that's going to have the tendency to shift our equilibrium reaction back toward the reactants, right? And so equilibrium is being shifted toward reactants. So there's essentially less temperature to dissociate N2 and O2 to form NO. And so now you can see why, if you remember when we first talked about exhaust gas recirculation, we said that there's two reasons why engine manufacturers use EGR. The first was an efficiency aspect, but the second, of course, is what we're looking at right here, right? And so EGR is very commonly used, particularly in diesel engines, to decrease nitric oxide concentrations. Okay, so very often students will pick up on the observation. They'll make the keen observation, if you look real quickly, that that peak flame, or that peak NO concentration is shifting towards stoichiometric as we go to higher and higher equivalence ratios. And again, it's ultimately, whenever you look at these results, what you'll be able to argue is there's a shift in equilibrium here, right? And so as we increase the EGR level, we're decreasing the temperature, and so the equivalence ratio, because of that decreased flame temperature, the point at which you have a high enough temperature to cause dissociation of N2 and O2 into NO begins to shift closer and closer to stoichiometric, right? So let me explain what I mean by that by looking at the notes, right? So if we look at say adiabatic flame temperature versus phi, right? And suppose this is 1.0 here. And so this is our adiabatic flame temperature for a given EGR, say 0% EGR. And then this is the adiabatic flame temperature for, say, 20% EGR, right? And let's suppose that, you start having fervent NO production at this flame temperature here, right? So this is the adiabatic flame temperature where, there's noticeable NO formation. Well, when you increase the EGR level, that temperature shifts to the right. Right? It's shifting closer to stoichiometric because the EGR is causing an overall lowering of the flame temperature. And so shifting that point in which you reach this absolute point, this absolute temperature at which the equilibrium starts to really kick in, right? That dissociation effect really starts to kick in, that equivalence ratio at which that temperature occurs shifts closer to stoichiometric, right? And so that's basically what you're seeing here as we go to higher and higher EGR levels. That peak NO concentration is shifting towards stoichiometric because that's the equivalence ratio where the temperature is high enough to result in that fervent dissociation of N2 and O2 into nitric oxide. Okay? Okay, very good. Well, so you now at this point, you are able to completely write objective number 1 of Lab 3. And so we'll now start to shift gears to focusing on objective number 2 of Lab 3 and also begin our discussions of the Chapter 5 material, the fuel air cycle analysis material. And one of the first things that we'll do, sort of still part of the Chapter 4 notes, is go back and now define these efficiency terms that we had already used before, but now relate them to something which we can actually calculate in the model, right? And so remember that fuel conversion efficiency is defined as the work per cycle, right? So this WC, it's a little bit of bad nomenclature, but this WC is the work per cycle, not just the compression work. And that's divided by the energy delivered. Remember that mass of fuel times heating value is the energy that's delivered, okay? But not all of the energy that's delivered will react. In other words, not all of the energy that's delivered will be released. There can be a combustion inefficiency that is a fraction of the delivered fuel that doesn't even combust. It doesn't even oxidize, okay? Now that we can do rich combustion reactions, we know that there's going to be a fraction of fuel that's provided in the mixture that its energy never gets released, right? And so that's what combustion efficiency is describing, is it's describing how much of this energy that's been delivered actually burns during the combustion process, okay? And so what the combustion efficiency is describing for us in words, right, is in the numerator, this is the difference between the enthalpy of the reactants and the enthalpy of the products. And if you remember way back when, we defined the heat of reaction, QRP, to be the enthalpy of the products minus the enthalpy of the reactants. And then we defined the heating value of the fuel to be the negative of the molecular weight, negative of QRP divided by the molecular weight of the fuel, okay? And just to be very clear, this is H bar products minus H bar reactants, where the units on all of these terms is kilojoules per kilomole, right? And that's why we introduced this molecular weight of the fuel, since the units on heating value are, say, kilojoules per kilogram, for example, okay? So if you look closely, you'll notice that this is HR minus HP as opposed to HP minus HR. And so the reason why we've done that is there's this minus sign here, and so we've just integrated that minus sign already into the calculation of combustion efficiency so that it's reactants minus products, as opposed to how heat of combustion is actually defined, where it's products minus reactants, okay? So the numerator, this numerator ends up being the energy that's combusted or the energy that's released, okay? So the energy that's released during combustion. And then the denominator is the same as in the fuel conversion efficiency definition. It's the energy that's delivered. And remember that fuel conversion efficiency is, what we get, right? So what we get is the work of the cycle divided by what we pay for, which is the energy that's delivered, okay? So that then allows us to define the thermal efficiency, the thermal conversion efficiency. And so the thermal conversion efficiency, A to T, if you remember, this is going to be what we get, the work that's the work from the cycle, divided by the energy released. Not the energy delivered, but the energy released, okay? Well, what is the energy that's released? Well, the energy that's released is the numerator of the combustion efficiency equation, right? And so this thermal efficiency is equal to the work of the cycle divided by the enthalpy of the reactants minus the enthalpy of the products, okay? The energy that's released. Okay, well, so we can then relate fuel conversion efficiency to thermal efficiency and combustion efficiency, where now what we get is the work of the cycle divided by the energy that's delivered. This is all equal to the thermal efficiency, which is the energy that's released, divided by the energy delivered, times the thermal efficiency, which is the work of the cycle, divided by the energy released. And of course, you can see that the energy released cancels itself, and so you get work over energy delivered is equal to work over energy delivered. And so the fuel conversion efficiency ends up being the combustion efficiency times the thermal efficiency, okay? And so we're going to come back to that again when we start the Chapter 5 notes and we start to do actual analysis with our fuel-air cycle analysis, okay? But what's kind of interesting is that now that we are able to quantify combustion efficiency as being this enthalpy of the reactants minus the enthalpy of the products, and we would use this expression here to determine that enthalpy of the reactants minus the enthalpy of the products, or at least one minus that, we're then able to plot combustion efficiency as a function of equivalence ratio, right? And so again, this is data that was taken a long time ago by Dr. Haywood at MIT. It's a fairly old set of data, but it's pretty interesting to note that when you go to very lean conditions, right? And so this would be lean on this side of stoichiometric. You'll notice that our diesel engine data points, right? So the X's, they all generally stay pretty high, right? Combustion efficiencies that are, say 95% and greater, except for a few when you get to very lean conditions where there might be some misfiring issues there, but still generally above 90%, okay? And of course, diesel engines don't operate close to stoichiometric, and so you'll notice that this is one of the last data points where equivalence ratio is about 0.75 or so. That's about as rich as you can often get with a diesel engine. And so a lot of this data that you see all scattered up in here, this is all spark ignition engine data that's all lumped together. And notice what happens is you go to very rich conditions, that combustion efficiency is decreasing precipitously as you go to richer and richer conditions, right? And so generally speaking, combustion efficiency as a function of equivalence ratio, where say this is equal to 1.0, more or less looks something like this, okay? And so we're going to come back to that concept here in a little bit as we start our Chapter 5 analysis, fuel air cycle analysis, and consequently actually do these calculations using the fuel air cycle analysis. All right, well, that completes Chapter 4 for us. So let's go ahead and start to dive into Chapter 5, which again, Chapter 5 is now the combination, the thing that we've been building up to for literally the last 8 weeks or so, right? So again, if you remember, we did heat engine analysis where we assumed ideal air model behavior, right? Open system. So this was basically ideal air heat engine analysis. And then we learned a lot about combustion, right? Where we actually have a fuel and air mixture, okay? Where here, when we do ideal air analysis, we basically assume constant properties of the mixture. But when we do that we can't possibly do that for fuel air analysis because the mixture is changing, right? As the mixture undergoes reaction from reactants to products, it's not possible for us to assume constant properties. And so we have to address that fact that the mixture is physically changing, chemically changing from reactants to products. And that forces us now to capture those changing properties. And that's essentially what we do when we do things like enthalpy of formation plus sensible enthalpy to characterize the thermodynamic properties of the mixture. So we take this heat engine analysis, we take this information about combustion, we add them together, and what we get is what we call fuel air analysis, okay? And fuel air analysis is now resolving that last deficiency that we had when we did the heat engine analysis. Remember that heat engines are not IC engines, and IC engines are not heat engines, right? And so we now are getting ourselves to the fuel air cycle analysis where we can have at least a thermodynamically correct representation of an IC engine, right? So the fuel air cycle analysis is a thermodynamically correct IC engine analysis. Okay, so because of that, a lot of what we assumed before when we did heat engine analysis, right? Some of the assumptions that we made, maybe we didn't go over these in great detail at the time, but one of the major assumptions that we made from heat engine analysis was that the properties of the mixture do not change, right? We were able to do things like assume constant specific heats, right? We would say change in internal energy, delta U is equal to CV delta T. Well, we can no longer do that when we do fuel air cycle analysis, right? Because the mixture is changing as we go from reactants to products. That also means that the properties of the mixture are changing, right? If the species are changing, then that necessarily means that the properties are changing. And so we have to capture that, okay? And so the way that we set this analysis up, it's going to look very similar. It's going to look very, very similar to the heat engine cycle analysis that we did with Chapter 3. But one of the big differences is that unlike the heat engine analysis, where we had a heat addition, and when we did the closed cycle analysis, we would have a heat rejection process, we no longer have any processes that allow there to be heat transfer. Okay, so our quote-unquote heat addition process, which doesn't exist in the fuel air cycle analysis, is actually an adiabatic combustion process, right? And so there is no external heat addition. The energy that is released during the cycle is in the fuel, right? So we literally have a fuel-air mixture. So we bring that energy into the cycle with the intake process, and we then allow that energy of the fuel to release during a combustion process, as opposed to adding that energy in the form of thermal energy during the heat addition process, which is what we did with the heat engine analysis, okay? So despite that, we are still going to have that combustion process take place under very specific conditions, right? Prescribed conditions. And so we're either going to allow there to be constant volume combustion, constant pressure combustion, or limited pressure combustion, right? And conceptually, these would be the same as constant volume heat addition, constant pressure heat addition, and limited pressure heat addition, okay? Now, of course, as many of you probably know, the actual combustion process in a real engine doesn't take any one of these forms, right? It doesn't have constant volume combustion. It doesn't have constant pressure combustion. It doesn't have limited pressure combustion, okay? And that's what we're going to talk about in the next chapter. In Chapter 6, we're going to talk about what real combustion actually looks like, right? The physical, and start to characterize the physical time it takes for combustion to occur, okay? We do allow the products of combustion to achieve and maintain equilibrium, including during the expansion process. And then finally, the rest of the cycle is very similar to what we had talked about in Chapter 3, the open cycle analysis, where we have an ideal blowdown process, we have the constant pressure exhaust displacement process, and then we have the constant pressure intake process, okay? And of course, really what this is fuel air cycle analysis is an improved prediction of actual IC engine behavior, where we can, for example, vary compression ratio, we can vary fuel air equivalence ratio, and we can vary EGR level, okay? And these are the things, for example, that you'll be looking at in objective number 2 of Lab 3, okay? All right, well, that I am officially out of time. I've used up my 50 minutes, and so we'll stop here. We'll pick this video up on Monday, very quickly go through the development of the fuel air cycle analysis, and instead leave sufficient amounts of time for us to actually go through the characteristics of the fuel air cycle analysis, which is what you'll be doing for your lab number 3, objective 2. Okay, thank you all so much for your attention, and I wish you a great rest of your day. Take care. Bye-bye.